Everybody, I'm going to go over radical chain reactions, which are the next little section that we're going to cover. So I'm going to kind of do an overview of the reactions that we're going to see this week. So I kind of broke them down by reagent and kind of what we're going to be seeing. And we're going to talk more about radicals and kind of how they're used, but you'll kind of get the swing of things once we start talking about the mechanisms. So the important thing to know about radicals is they are not like the polar mechanisms that we've been doing so far. We're not talking about electron pairs moving. We're talking about single electrons moving. So keep in mind that it takes 2 electrons to form a sigma bond. So we're going to need to have something happening to make it so that one electron is going to meet up with another electron to form a bond. So these are the different reagents that we're going to be using. So we're going to see Br2, HBr, NBS, which I'll talk about what that is, and tributyl tin hydride. Okay, so these are the ones that we're going to cover. This one shows up only in the problems in your book, but I think it's a really important one and has done a lot of really neat chemistry. So we're going to cover it too, but we'll probably hit that on Thursday, not tomorrow. So the bond broken, that's going to kind of help guide us to figure out really what's going on. So the important thing to keep in mind here is that with Br2, this is actually a reaction of alkanes, which is not very typical from what we've seen so far. So it is a reaction of alkanes. We will be forming carbon radicals and then eventually forming a carbon-bromine bond. With HBr, this is a variation of the reaction with alkenes. So we will have alkene starting materials, we'll use HBr, and we'll actually go through a radical mechanism rather than the polar mechanism that we've covered so far. Because if you look at the bonds formed, they are the exact same bonds formed as when we just did an alkene with HBr, but you'll see that there's definitely a difference there. With NBS, NBS is N-bromosuccinimide, and it is another bromination type of reaction, and it specifically brominates allylic or benzylic CH bonds to make new carbon-bromine bonds. And then the last one, which is really interesting, it uses carbon-halogen and carbon-carbon pi bonds to make new carbon-carbon sigma bonds. So it's a really nice reaction to make carbon-carbon bonds. So we're going to talk about each one of these in turn. So I'm going to start with the bromination, so the Br2. And just like I said earlier, we are going to be using alkane starting materials here. So this is a reaction that alkanes can do, which is not that common, to be fair. So every radical reaction really needs just some way to get the radicals started. So in this case, it's generally going to be light or heat. So if you heat this up pretty high or you shine light on it, then you can get Br2 to do a homolytic cleavage and break into 2 different bromine radicals rather than the one bromine molecule. So if we start off with Br2 and we have our heat or light, then we can have this split right in half, and each of those bromines is going to get one of the electrons from that sigma bond. Okay, the radicals are denoted by just a single dot, and it is really important to draw in the radical, otherwise we won't know what it actually is. So this radical is going to go get a hydrogen to do a hydrogen abstraction. So I have a whole bunch of different hydrogens on this molecule. So these are all the types that I have, really. So I've got secondary hydrogens, tertiary, and primary, okay? So I have all these different options of which hydrogens I can actually do the abstraction on. What we're gonna wanna go for is we want to target the more substituted CH bonds, okay? Because if once we do this, so if we target that CH bond that's the tertiary one, that's going to give us a tertiary radical. So we can get to that tertiary radical. This is the more stable radical. And that's the one that we want to be forming, okay? So that's our carbon radical intermediate. So if we look up here, that radical intermediate, that's where we're at right now. We just broke that CH bond. So we've got our carbon radical, and now this step, so I guess I should label these. So this is the initiation step. Right, that's what's actually clear. I don't know if that helps. Let me try again. Okay, so that's our initiation step. And then the next step that we're about to do is our propagation step. So we are propagating the radical by creating another reactive radical. So that carbon radical can then react with a molecule of bromine. So if we come here, one of those bromines can make a bond. The other bromine gets the remaining electron from the bromine-bromine bond. Actually, I'm going to change that arrow. So we're going to get that brominated product plus Br radical. And that Br radical, that's our propagating radical, because this is our propagation step. And this Br radical can come right back to here and do this step all over again. And we're just going to keep on going around and around until we have no bromine left. Okay, so that's how the bromination works on alkanes. Let's move on to talk about HBr. Okay, so I'm just going to use a really, really simple alkene here. So I'm going to use HBr and I'm going to use a peroxide. Okay, so in this case, our peroxide is going to be our initiator. So that's going to be the thing that is actually making our first couple of radicals before our propagation step takes hold. So our product here is we're going to be putting our bromine on the least substituted side of the alkene. And you'll see why that is in a second. So our initiator, that's going to be our, I'll do it down here. So our initiator is our peroxide. So the first step there is we're just going to split this open just like we did with the bromine. And this happens because, again, that oxygen-oxygen bond is quite weak. So it's easy to make into radicals. Okay, so we've got 2 oxygen radicals there. And then one of those can react with HBr. We're going to do a very similar hydrogen abstraction that we just saw in the previous example, where that oxygen radical is going to go grab that hydrogen atom. So we're going to grab the hydrogen atom. The other electron ends up on the bromine. So that formed an alcohol and our Br radical. Okay, So I'm going to show a different way of drawing out the mechanism here. So this one I kind of showed that it's cyclic by drawing the bromine radical as a product to show and kind of make it very clear that I'm going to keep on going with that radical. In this one, I'm going to do it cyclic. So I'm actually going to show it in a circle. So once we have done that initiation step, okay, so initiation is just the process of creating the first radical. So once I have that initiation step done, then I can go ahead and do the main reaction part, which is my propagation step. So if I start with my bromine radical, the first thing that's going to happen, I'm going to try my best to draw a nice circle. We'll see how it goes. So we're going to have our alkene come in. So our bromine radical is going to go react with that pi bond, okay? So we're going to have the bromine is going to go grab one of the pi electrons and make a new bond. And then our other electron of the pi bond is going to end up on the carbon, okay? So in this case, again, we want to form the more stable radical, which is the more substituted radical. So we're going to have our radical. Let me try this again. I just need to move this arrow. Okay, so we're going to put that radical on the carbon in the middle to form the more stable, more substituted radical. So I'm going to end up with something like that. So if we look here, we've got carbon, carbon, bromine with the radical over here. So that is denoted by this radical intermediate where you already have the bromine added when you have your intermediate as the radical. Okay, so we have that radical. We just need to have a hydrogen there really to finish this off. And we know where the hydrogen is going to come from. It's going to come from HBr. Okay, and that's going to be finishing off our propagation step. So we're going to have HBr. We're going to do another hydrogen abstraction here, where that bromine is going to get the electron. The H is going to end up on the carbon. So we're going to end up getting that product out. And in the process, we have made more of our bromine radical, which can then go react with another equivalent of the alkene, and we go on and on our merry way. Okay. So if you look at your book, they do talk about termination steps here to finish off the radicals and to get the reaction to stop. I'm not going to focus on that at all because it's really easy to just do a termination step too early, and then you don't actually have your reaction occur. So we're going to stick with the initiation and the propagation steps. And we are not going to talk about the termination steps. Okay, and again, we're going to form the more stable radical. Ooh, goodness gracious. Okay, so let's move on to the N-bromosuccinimide. So this is frequently called NBS. It's kind of a long name, but N-bromosuccinimide is how you say it. So for this reaction, this one is kind of a special one. So if we take the same alkene that we did before, and we have NBS, and we'll add heat or light again, and I said those backwards, I do every time. Then we can end up getting an allylic bromination, okay, or benzylic, depending on what you want. So the structure of NBS is this. So it does have an N in it, so that's at least something. And it does have a bromine. Okay, so we've got a nitrogen bromine bond. It is not a strong bond. And because it's such a weak bond, we can use light or heat to do a homolytic cleavage on it and create radicals. Okay, so we can make a nitrogen radical and a bromine radical. So this nitrogen radical is pretty stable. It is pretty nicely resonance delocalized. You can imagine this kind of situation. It's kind of the, radical version of the regular amide resonance structure. So we have our bromine radicals created from that. So the thing that can be a little bit confusing is that we look at this, we see that we have the same propagating radical in bromine radical, but we have a very different reactivity, right? Because all we're doing is we're taking one of the CH bonds and making it into a carbon bromine bond. We aren't actually touching the alkene, which seems kind of odd considering this, which also uses a bromine radical, also has a pi bond, but uses that pi bond. And it's kind of a little bit similar to this one as well, where we're just using a CH and getting the carbon bromine out. So it's kind of a combination of the two, and you'll kind of see why as we go through the mechanism here, because there's actually Br2 and HBr involved in this reaction, all through this one reagent of N-bromosuccinimide. So we're going to start off with our bromine radical. I'm going to do it in a circle again, and hopefully I can make a better circle than I did the last time. We shall see. Okay, so we're going to start off with our alkene. And this time, instead of going straight for the pi bond, we're actually going to do a hydrogen atom abstraction. Okay, so we've seen those a few times now. So we're going to go get that hydrogen atom and end up with a carbon radical. So down here, we're going to have our carbon radical. And then over here, we've made HBr. Okay. So at this point, you're looking at it going, well, I should be able to do, an alkene reaction with that HBr, but something else happens instead with that HBr. So over here, N-bromosuccinimide is actually going to react with HBr. So if I've got NBS and HBr, we know that HBr is an acid. So we're going to protonate the most acidic atom, or we're going to protonate the most basic atom, which is one of our oxygens. Doesn't matter which one, they're both the same. So we're going to protonate there. Okay, we can draw a resonance structure of that. Okay, so essentially what we have here is we formed the whole piece here into a pretty good leaving group. Okay, so if we attack that bromine, we can kick off all that other stuff. And so what happened is we also made Br minus, so that Br minus can come in, attack the bromine, electrons move over onto the nitrogen, oops, and we've made Br2, okay? So that Br2 is going to participate in this reaction at this next step. Okay, so we're actually going to be making our propagating radical from Br2. So we're going to bring Br2 in here. So we're gonna break that Br2 in half. One of the bromines is gonna go onto the carbon radical to give us our final product. And one is gonna be making our new propagating radical, okay? So the only time that we've actually done the initiation is right at the beginning. We're gonna make a small amount of those nitrogen and bromine radicals. And then everything else is going to happen once you make that equivalent of HBr, then you're gonna be able to make one more molecule. So one molecule of HBr is gonna go to one molecule of Br2, so you can make another molecule of product. So never at any point in this reaction do you have a buildup of HBr or Br2, which is why you can see that alkene stay present, okay? Because we're never building those things up. The other thing that's important to notice here is that that radical that we formed on the carbon is resonance stabilized. Okay, so we can draw a resonance structure here. So if you imagine an instance where my alkene was not symmetric like I have it here, we could see reaction happening here. So we do need to watch out for product mixtures from unsymmetrical alkenes. Okay, so that's NBS, definitely a little bit special, definitely different than the HBr or the Br2 reactions. Okay, so then our final reaction that we're going to cover is our carbon-carbon bond forming reaction. So we're going to use a carbon, an organic compound that has a halogen and an alkene in it. That's kind of the two things that you need. And we're going to use tributyl tin hydride and some sort of initiator. Okay, so there's a bunch of different initiators that we can use. We'll talk about some in class. But at the end of the day, this is really good for making rings. So this particular one is going to make this cyclopentane product. And so the way that it does that is just like previously, we have to go through an initiation step. Jeez. Okay, so whatever initiator that we've picked, you know, there's a bunch of different types. It doesn't really matter which one. All it does is it just needs to make a radical easily. So we can make, once we have made our first initiated radical, that can react with our tributyl tin hydride. Okay, so we're going to do a hydrogen abstraction again. So the initiator is going to take the hydrogen, one electron is going to end up on the tin. So we can get to our tributyl tin radical, okay? So that's going to be our propagating radical. We're going to see that get regenerated. And the nice thing about radical reactions is, yes, they are definitely different than what we've done before, but they have such a good check in place of, if you did the reaction right, you should be forming Br radical or tin radical. Like, those are the only two propagating radicals that we're going to talk about. So if you form something else as a propagating radical, something probably went wrong. So that's going to be our check. Okay, so we're going to do another cyclic one. Okay, so we're going to start off with our tin radical. I'm going to try to split this into thirds, so we'll see how it goes. So we're going to start with our organic compound. So it's important to keep in mind here that the first step, we're going to write up the steps over here. So the first step is form the tin radical. Second step is going to be form the X tin bond, okay? So the other way you can think about this is break the CX bond, okay? So in this case, X is gonna be a halogen. It's often gonna be bromine, but it can be other halogens as well. So the first thing that we're gonna do, we're not gonna go for the alkene, we're gonna go straight for the halogen. The reason for that is that the tin halogen bond is a lot stronger than a tin carbon bond. So we're not going to be going for the carbon with the tin, we're going to be going for the halogen. So that tin radical is going to go grab the halogen and make a carbon radical in the end, okay? So that comes out as tributyl tin bromide and has made a carbon radical, okay? So now this carbon radical has to react with something. It's not happy this way as it is. So we have to have something else happen, and that's where our alkene is going to come into play. So we're going to have our carbon radical go do a reaction with a pi bond. And in this case, 1, 2, 3, 4, 5. I've got 5 carbons in this chain. You can imagine that I can have that carbon attached to this one to make a 5-membered ring, or this one to make a 4-membered ring. We are always going to be going for the more ideal ring size. 4-membered rings are really, really hard to form. We're not going to form 4-membered rings with this, this methodology. So we're going to form our bonds, and that also has made a more stable radical, which is a benefit. So I've formed my 5-membered ring, but I still have a radical there. I'm actually going to draw it over here just so that it's a little bit closer. Okay, and then we just need to do our final propagation step. So we're going to be bringing back in our tributyl tin hydride. We're going to do a hydrogen abstraction like we've done a bunch of times now. And then that's going to remake our tributyl tin hydride radical, our tributyl tin radical, and give us the H that we need to get back to, no radical product. So we formed the product, we formed our propagating radical, and we made it out the other side. Okay, so I guess the second step would be C radical reacts with pi bond, and then C radical abstracts H from the tributyl tin hydride. There we go. Okay, so the thing to keep in mind here, these are very frequently used in ring forming reactions. So the general rules for ring formation for these ones, it's really all about kinetics. So it's about which ring is going to be formed the fastest, the easiest. So we're pretty much going to be looking at stuff where we can form 5, 6, and 7-membered rings. And then within those, when you have to decide between a 5 or a 6, the rates, a 5 is going to be faster than a 6. 6 is going to be faster than 7, and 7 is going to be faster than 8. Okay, so if you think about why that is, you think about a really long chain, it's just about how much of the time is it spent with close proximity of the two ends that need to actually meet up. When that chain gets smaller, that's easier to do, right? So a 5-membered ring is easier to do than a 6, even though a 6 has a little bit less ring strain than a 5 still doesn't have that much ring strain and has a shorter chain length to get the two ends connected. So that's what we're going to be practicing more this week. And we'll go through all of this in class again, but this is hopefully just a little extra bonus to get a little preview in. So I will see you all soon, and we will talk about radicals.